All right, so now we're going to get into Cavalier's principle. And this is the principle that I talked about in the last slide, meaning that whenever you're calculating the volume of a cylinder, you're not talking about the slant height. You're actually talking about the height at a 90-degree angle to the base. So let's get into that. And this activity is actually really good at explaining why Cavalier's principle works. So let's take a look at a stack of identical coins, CDs, any type of cylinder shape that's very thin, and it'll kind of show why it makes sense. So if we're looking at this is a cylinder, a right cylinder, meaning it's at 90 degrees, versus an oblique cylinder, meaning that it is slanted. Now, if you look here, if I were to keep this in a straight line, you'll notice that the height doesn't change, but it does change once I go up and down. And we'll see why that is by thinking about it in terms of stacks of coins. So if you stacked all these up perfectly, the height's the same, right? We still have this stack of CDs or coins or whatever you have here. If I were to slant them a little bit, the coins have not changed volumes. They've just moved over. So when you're thinking about this, you're thinking of millions and billions of coins or what have you, slanting over. So that's how come Cavalier's principle holds up. It's this idea that you're um, you're just having all these coins move, but those coins have not changed volumes, ergo, all of them together have not changed volumes. So that's Cavalier's principle in a nutshell. So think about the volume by definition of volume. What is the volume of a stack equal to? Express your answer in words instead of numbers. So begin stacking, read this. Think about the volume stack by definition. What is the volume equal to? So volume would be equal to the area. So, well, I'll say it all because we should be using complete sentences for this. Volume would be the area of the base times the area of the, or times the area, times the length of the height. Or I should say measured, times the measure of the height. Again, use your own words. I'm just being very, very picky with mine. Times the measure of the height. And use your own words because you're not learning anything if you're just going to copy down my words word for word. So if you see it a different way, it's like, oh, it's the bottom times the height, and that's your way of remembering it, go for it. I'm just using the formal definition because it just makes it easier to have formal definitions. So the volume is the area of the base of the height. And the reason why this is as area is how much space it takes up in 2 dimensions. And if we're multiplying it by the height, that's how much space it's taking up in 3 dimensions. And I can even write that down. So um, this is how much space the object takes up in three, oops, that's supposed to be an R, 3 dimensions. So one of them's kind of like the mathematical definition. This one's kind of like what is volume. I'm covering both of our bases there. Because technically I could just say this and have nothing to do with anything else. Now slowly move the disk over and lean it oblique. Be sure that the stack does not fall over. So we're supposed to be doing this like IRL with coins. You can do that if you want. But here we can kind of see what's going on. Does the volume of the stack change? No, the volume, and I went over basically the whole activity beforehand. So that way it's a little bit easier to understand instead of doing this piece by piece. Doing it piece by piece makes it a little harder. So the volume does not change. This is because the volume of each coin did not change. And since we have the same number of coins, the cylinder as a whole must have the same volume. So that's the idea there, is because we're not changing any of it, any of the coins or anything, there shouldn't be a change in volume. So how do we do in this one? So honestly, like to me, this was a little weird to understand Cavalier's principle, but once you see it, it kind of starts making sense. So I'm going to give myself a 4, and I'm basing myself more on the initial idea of Cavalier's principle where I didn't really understand it. 4, I didn't really understand it at first, but seeing the coins made the principle make sense. And if you're still having trouble like understanding it, it's fine. This is a good spot to kind of write down what you're having trouble with. Um, and you can even tell your teacher, I'm like, I was having trouble with slide 13 out of 24. All right, so, oops, didn't hit submit there, but all right, so let me scroll back up. So this is basically just a general idea of like what we've been saying. It's at the 90-degree angle, no matter what. All right, so now we're going to talk about cones. Now, the way I like to explain a cone is think of it as kind of like the triangle of a cylinder. Whereas a cylinder, you can, if you look at it from the side, you can be like, oh, that's a rectangle. And I'll show you what I mean in a second because I accidentally put my pen on the other side of my coffee. All right, so if we look at a cylinder from 3D, we have this. Oops, I might have to fix my settings here in a little bit. Give me a second while I fix my settings. So it wasn't really my settings that were off. It's the fact that I have my board at a different angle than the monitor, and that was really throwing me off. So if we look at a cylinder, from the side it looks like a rectangle, and with a cone, I told you guys you get to see my terrible 3D drawings. A cone, if we look from it on the side, it looks like a triangle. And the way I always have taught area of triangles and rectangles, this idea that a rectangle is length times width, and a triangle, we can think about it as half of a rectangle. It still has the length times width. Let me use a different color for it. Still has the length times the width, but it's half of it because this other triangle has a length and a width as well. Probably should have used a better color for that. Let's use orange. Length and a width as well, except it's kind of cut in half. It's easier to see it when you have like a right triangle because you can clearly see that it's cut in half. If I could draw perfectly, but you get the idea. It's cut in half. Well, that's in 2 dimensions. I can just do this. In this one, we have 3 dimensions. So that it's actually kind of interesting. So for a cylinder, our volume was pi r squared, the area of the circle, times the height, pi r squared times h. So for a cone, it's a third of it because if in 2 dimensions it was half, a triangle is half, in 3 dimensions, it's going to be a third. So a lot of times they write it as 1/3 times pi r squared times h. Sometimes they just write as pi r squared h. Everything divided by 3 because it's a third of it. Multiplying by a third is the same thing as dividing by 3. And we'll see how they prove it right now. Oops, let me erase this before we move on. So we're going to look at this, and they're going to want us to do several of these. I'm going to do 2 in the interest of time for this video. That way you don't see me just plugging in a bunch of numbers. So let's go into the simulator. So first I'm gonna fill out the ones for the cylinder first, and then I'm gonna fill the ones out for the cone. So first, you have to open up both of these. I'm gonna close this other activity. I have to open them both up. We have one for a cylinder, one for a cone. I guess I'll do the cone first because it comes up first, and then since I did cylinder first and then this, if you click it in order, it ends up working out perfectly. Um, so I'm gonna just pick numbers, and to make it easier, since I kind of gave you guys a little sample of what the formula we're gonna derive is, I'm gonna make all of my radii and all of my heights multiples of 3. So here I'm gonna put 9 for the radius, and I'm gonna put 12 for the height. Here I'll put 6 for the radius, and this one let's make it tall. Let's make this 15. So I'll do 2 examples here. Let's do the cone first. So the cone, I want my radii. What did I say my radius, or radii? Radius. What do I want my radius to be? I'm going to make my radius 9. So I'm going to drag this over to 9. Oops. And I want my height. What did I say I want my height to be? I want my height to be 12. And considering that the height and radius were different when I opened it, you could have literally just plugged in whatever was here and started it off there. I want my height to be 12. So I'm going to lower this down a little bit, make it go down to 12. Oh my gosh. Trying to do tiny move. I can only imagine how hard this is if you guys have to use a touchpad. Okay, so when I calculate my volume, I get 1017.9. So I'm just going to put 1017.9. Now I'm going to plug these in for the next one, 9 and 12. So 9 was the radius. So I'm going to move my radius to 9. Had it. There we go. And I'm going to move this down to 12. And I believe the default ones, whatever you open the tab with, are the same for both. So you might want to do that for your starting one. Just plug in whatever's already there and solve it. So if I do this, oops, 9.1. I don't know how that changed. There we go. 9 and 12. This one is 3053.63. 3053.63. So 3053.63. Now, this is what I think is weird, is instead of like, let's put the big number on top, they want to put the smaller number on top. So when you grab a calculator, I'm going to use this one, just because it's a little more convenient for me than doing this, and I like seeing what I'm typing in here. It's not a true scientific calculator, but I prefer it to having to use the Texas Instrument thing. So let's see what we have here. So we're going to do 1017.9 divided by 3053.63. And it looks like we get, I'm assuming they only want 2 decimal places, so it's still 0.33. And now I'm going to change this so my radius is 6 and my height is 15. So let's change the radius to 6 on both of them. 6, 6, while I'm here, might as well change this to 15. Oh, I see how it changes. So be careful when you're changing your height. I recommend changing your height first, actually, because your height can also change. Oh, never mind. I thought it could change the radius, but because I see that my radius did change when I started changing my height, but I don't know why it changes. So be sure when you're done, make sure that both your height, oops, I accidentally right clicked, your height and your radius are where you need them to be, because for some reason my radius keeps changing on me. It shouldn't make, well, actually, it would make a big difference because we're squaring the radius. Um, but for height, it doesn't matter as much. Radius is a little more crucial because of the r squared. You're squaring that 6. All right, and then we're going to change this. I'm going to make this 15 right now, just more because it's fresh on my mind. The radius is 6, so we already did that. And it's going to be 565.5. Okay, so I'm going to do 565.5. Perfect. And then this next one, my volume is 1696.46. 1696.46. 1696.46. The reason why you see me not saying like 1696.46 is it's easier to remember things if you do it in little chunks. So that's why I do it 2 digits at a time. It's easier for me to remember 16 than 1600. So 1696.46. Uh, and this should still be that 1/3. And this is the reason why I'm not doing all 5 of them. You see 2, you kind of get the idea. So we're going to do 565.5 divided by 1696.46. And we still get that 0.33. So 0.33. And this is 1/3. So based on the things, what can we do to find the exact value? Keep in mind that volumes are recorded and rounded, not exact values. So the reason why they say they're not exact values is because, especially when we're dealing with circles, pi just is always going to be an approximation. No one's ever going to write out pi. You can never get the exact circumference or the exact area of a circle, because no one has ever finished pi. So when we're doing these, we'll see that it's 0.33. So it's about 1/3, which is what I mentioned before. So what we're going to say is the volume of a cone is about 1/3 of the volume of a cylinder, which I think is pretty interesting. It's interesting to see that. Um, and this one, I'll say, it's kind of hard to explain. So I would actually give myself like a 3 for the beginning. Doing the activity itself, I'm doing pretty high. So it's important, everyone, to just realize that a self-evaluation isn't really like your score for the activity. It should be, it's an evaluation. It's you understanding the material. So you have to be critical with yourself. If you did this and you have no idea if you answered it right, give yourself a 1 and explain why. Why you think you just like your understanding's at a 1. So I'm gonna do 3 to 4. 3 to 4. The idea of volume being 1/3 is very strange. Strange. But I did understand the activity well. So just write what you honestly think you did about that and submit it. So let's take a look at our next shape. So basically this 1/3 thing, they don't really explain why it's 1/3, which is one of the reasons why I explained it, but at least you get your formula afterwards. And they use it as you multiply 1/3. I like doing it as you do the whole thing and then you divide by 3. I think Google even does it too. Let's see what Google does. Volume of a cone. Yeah, Google has it as you take the height divided by 3. Dividing the height by 3 is the same thing as dividing everything by 3. So um, I don't know why Google has it that way. It's strange, but either way, no matter how you do it, it's fine. Now we're going to be talking about pyramids. So pyramids are interesting as well um, because of the fact that it's essentially a prism. So remember we talked about rectangular prisms earlier, where rectangular prisms are, oh, I totally did this wrong. I forget how to do these. I remember one of my art teachers said, actually, I don't think it was my art teacher. I think it was my architect teacher. You start with a rectangle, you draw your lines going this way, you connect these, you then do this parallel to that line over there, make sure they're the same lengths, draw a line over here, and then what you can do too is have a dotted line at the same angle as this line over here, and make this parallel to this line over here, and then you can just do this line, and it should be parallel to this line and the same length, and there you have a prism. Um, you can probably draw it a lot better than me. I'm writing on a tablet that outputs to my monitor, so it's kind of weird because I'm not physically touching uh, the exact drawing. Whereas if I was writing like on a notebook or something, like my pen is actually drawing it, but it would still look terrible, so it doesn't matter. A pyramid. So let me draw a pyramid. So a pyramid, if we were to draw it out, is essentially that prism, just about a third of it because of the fact that there's triangles. And I guess it also depends on how many faces you have. By a face, I mean this triangle right here, how many faces we're dealing with. So let's kind of see how they calculate these faces. All right, so side of base. So by side of base, they're talking about, we're assuming that these are squares. So that's why we're looking at a volume of a cube. We're assuming that every face is a square. So the side here and the side here are the same as the height that we're going to talk about. And a pyramid, uh, do we talk about how many sides we have in the pyramid? We don't. So for this pyramid, we're assuming a square base. So we're assuming that the base is a square. So obviously, if the base is a square, we're going to have 4 faces because there's 4 sides. So again, I'm only going to do a few of these. You can guess that if a cone was a third, probably going to be dealing with a third here too. So what I'm going to do is I'm going to keep these all multiples of 3. So side length, 3. Height, let's do a height of 6. Why not? Side length of cube, that's a little weird. So I'm going to make it the same as the side lengths of a pyramid, because so basically you should always have your side lengths of your pyramid the same as your side lengths of a cube. Otherwise, this doesn't really work. So This column should always be the same as this column. The fact that they didn't do that is kind of dumb. So you're going to do 3. So I'm going to do this one as 6. I'm going to leave the height as 6. I'll leave that as 6. This one, side lengths, I'll do 6 here. I'm going to make this a 9. I have to make this a 6 in turn. Um, Actually, you know what? Let's skip this one just because I do not like that number. But we'll do in 2 examples. This should work. So let's click on our things. Let me close these out. So, and we're gonna do, they want us to do pyramids, so I'm gonna click, oh, I see what they're doing. If you click this first and then this will be your newest tab. So that's why you're doing the pyramid first, and that's why you're doing the cube second. So just click them in order, and your tab should be in the same order. All right, so this one, we're doing 3 and 6. So side length is 3. I'm starting to think that was a little too small. 3. Okay, cool. And height is going to be 6. There we go. So 3 and 6. You know what? I always find it funny that we're supposed to be deriving the formula, and the website they give us clearly shows the 1/3 right here, and it clearly shows length times length. So yeah. So we're going to get 18 for this. Now we're going to do volume of a cube. So if we do volume of a cube, we're just going to move this down to 3. And this one, I don't know why they give us a simulator, but at least we can see the squares. If we were to count all the squares in this, we would see that it is 27 squares. So I'm going to write this down. Oh, and also you can see it right here, 27. 27. So again, they're doing the smaller one over the bigger one, and I'm not even going to calculate it out. It's 0.333. Basically, this idea here is if you're dealing with a cylinder and you're dealing with a cone, this is always, assuming that the height and the radius are the same, it's always going to be 1/3 of it. So this times 3 is going to give us that. Same thing with a pyramid. A pyramid, ooh, that looks terrible, is always going to be, whatchamacalled, um, sorry, I'm like losing track of what I'm doing here, is always going to be 1/3 of this. Assuming that the height and everything are the same, I drew this too tall. So if you take that times 3, you get that. That's a basic idea of what we're learning here. So what do you see here? So we're going to say that a pyramid is always a third of a cube, assuming the side length and height are the same. And the reason why I say side length and height is I'm going to change this cube to rectangular prism. So this doesn't just apply for cubes. The only reason why they did the cubes is laziness, I guess, because you can do this for a rectangular prism. Let me see if they have the actual, they don't have the thing. Oh, that sucks. You can change the side lengths here and change the height here, just like you could change it for here, and it would still work out perfectly. They just choose not to do it here for some reason. So yeah, that works out. And for evaluation, you can just probably give yourself a 5 if you really made the connection. Like, wait a minute, this is kind of like a triangle. The other thing was kind of like a triangle, and so on. All right, and here they kind of, oops, let me erase this. Here they kind of show you the property as it is. As long as everything works out the same, everything should work out. So, moving on. What's the formula for a pyramid? So if we look at this, it's side length times side length, so side length squared times height, and it's a pyramid. These are triangles in 3D, so we're going to divide it by 3. So it's side length times side length. Um, Let me write that down because I picture it in my head. Side length times height. And all of this is going to be divided by 3 or multiplied by 1/3, however you want to see it. So this becomes side length squared times height divided by 3. Now, if we look here, we're kind of seeing, oh, there it is, the 1/3. So we want this 1/3 here. So we're just going to click that, boom, and we're good. We literally just did it in the last activity. So let's go to the next question. So, and again, whenever we're talking about height, Cavalier's principle works out for these shapes as well. You want the 90-degree angle height, not the slant height. First of all, this slant height is not going to be equal to that. We'll talk about it in other topics, but this height and this slant height doesn't equal each other here. This is going to be half the length because remember we have this other half over here. Um, and this should look familiar because this should be a squared plus b squared equals c squared. So we're going to use the Pythagorean theorem whenever we're going to talk about slant height. So those will come into play, but later. But just remember for now, we want the 90-degree angle height. We want the actual height when we're talking about height. Height at a 90-degree angle. All right, and let's see here. And here's the summary. So I would write these down in case you guys need them. They're very useful formulas, and they'll help you out during the mastery test. All right, guys, so that is our first module for Unit 2. Hopefully you guys were able to find this video okay. If you're in my class, obviously I'm posting it in the same Google Classroom. If you're not in my class, um, it, I mean, it's just semester B. I just wanted to separate the videos in a different playlist. But, all right, guys, hope you guys are having a good start to a new year. Um, See you guys in the next video.